Okay, if we know the atomic radius is half the distance between two nuclei of identical atoms. Okay, so let me just draw out, like, you know, here's a hydrogen atom. Here's a hydrogen atom. They're bonded together, okay, because they're right next to each other. They're bonded together. So the distance or the atomic radius that we're talking about, here's the nuclei of one hydrogen atom, here's the nuclei of another. If I connect that, that's the distance between the nuclei, which means the radius, the atomic radius, is half that distance. Okay, right? It's essentially the distance from the nucleus to the edge of one of the atoms. The reason we have to write the definition this way is that it's really hard to tell where the defining edge of the atom is, right? Because we know how electrons work now. They sit in atomic orbitals, right? They sit in orbitals, which means they could be bouncing around all over the place within that orbital. Do you agree? Remember that interactive display we saw where we added our orbitals, then we added our electrons, and they bounced all over the place. That means it's really hard for us to find the definitive edge of the atom. So the way we measure atomic radius is we take the distance between the nucleus of two identical atoms, and we take half of that, right? And we say that's about where one of our hydrogen atoms ends. Does that kind of make sense? Why do you think it has to be written that it's two identical atoms that are bonded together? Why do you think it has to be written like that? Why could it be two different atoms? Yeah, perfect. Different atoms have different sizes. So if I am comparing hydrogen, which only has one shell of electrons, right? Hydrogen is on the first energy level, so it only has one shell of electrons. If I'm comparing that to potassium, which has 4 levels, right? Potassium really has 4 shells. So if I take the distance between those, and I say half of that distance is the atomic radius, that'd fit here. Is that really how big hydrogen is? No, right? So do you see the difference there? We have to look at two identical atoms to be able to tell a definitive how big our atom is. Okay, does that kind of make sense? All right, so the trends on the periodic table. I'm going to pull up a blank periodic table here so I can show you a little bit bigger. Trends on the periodic table for atomic radius. All right. I'm going to always draw my trends as an increase. Okay, so it increases in the direction of my arrow, and I'll explain why that happens. So atomic radius increases to the left and down. Okay, to the left and down on the periodic table. So you need to draw that on your periodic table, and you can either draw it like that, or you can draw it, like this, or however you want to do it. But it increases as they go to the left within a row, and then they increase as they go down. So if I start with lithium, okay, or sodium or magnesium, whatever it is, if I start with one way on the left, we've entered a new energy level, right? Do you agree? As we go from hydrogen, or we go from the first energy level to the second, we add a shell of electrons, right? As you move down, you add a shell. So that automatically makes our atomic radius bigger, right? That automatically makes our atom bigger as we add a shell of electrons. Does that make sense? As you move down on the periodic table, you're just adding another shell. Okay, so that's why the trend down works that way. As we move left to right or right to left, that trend is a little bit trickier. Okay, as you move to the right, you see a decrease in atomic radius, right? These are smaller, and these are bigger. Okay, you can write that on your periodic table if you want, just so you remember. But these are smaller and these are bigger. The reason we see them get smaller as we move to the right is because let's just say I'm looking at lithium. Okay? And I'm going to draw a not realistic version of a lithium atom, but I want you to just see what's happening. Okay? Lithium has 1, 2, 3 protons in its nucleus. Do you agree with that? What's lithium's atomic number? 3. So it has 3 protons in its nucleus. Agreed? Which means a neutral lithium atom has 3 electrons. Right? As we move now from lithium to beryllium, I'm going to do that in a different color. Beryllium is going to be red. We add another proton. So as our positive charge in the nucleus gets stronger, it pulls the electrons a little bit tighter to itself. Okay? It pulls those electrons in a little bit closer. So that decreases our radius. As our positive charge increases by introducing a new proton, that means our electrons get pulled a little bit tighter. So next, as I move to boron, I'm going to put boron in yellow. As I move to boron, I add another electron, which then pulls our electrons a little bit closer still. That's why you see the atomic radius get smaller as you move to the right. Okay, as our positive charge increases, I'll write it out. As the positive charge increases, the electrons get pulled in tighter to the nucleus. Okay, so that explains why the atomic radius is bigger on the right side of the periodic table than on the left. Okay, so next we're going to talk about ionization energy. So ionization energy, its definition is the amount of energy required to remove the outermost electron from a neutral atom. Okay, the amount of energy required to remove the outermost electron from a neutral atom. All right, so I want you to think about if I remove the outermost electron from a neutral atom, what happens to that atom in terms of its charge? What does it become? Does it become negatively charged or does it become positively charged? It becomes positively charged. So I want to just put this up here. Removing an electron makes a cation. Removing an electron forms a positively charged ion, which we call a cation. Does that concept make sense to everyone? We take an electron away from a neutral atom. That means we have less electrons than protons, which gives us this positively charged atom. Agreed? The reason I tell you that is because it's going to help us look at our trends a little bit more clearly. Okay? So the ionization energy is the amount of energy required to remove the outermost electron. So what we need to think about here is which atoms want to give away their electrons and which don't. Okay, which atoms really easily give away outermost electrons and which ones don't. Okay, so I'm going to pull up my periodic table here again, and I'm going to show you the trend, and then we'll talk about how each trend works. Okay. Sorry, did we have what we needed on with the definition part of it? Or you need another second? We okay? Okay. All right, the trend for ionization energy. Ionization energy increases from left to right and bottom to top. Okay, ionization energy increases from left to right and bottom to top. Okay, so that means as we move to the top right on the periodic table, those electrons are really, really difficult to remove. Okay, they are really difficult to remove. So that means helium has the highest ionization energy, right? Oops. Helium has greatest ionization energy. Okay? To remove an electron, helium requires the most amount of energy. Helium wants to keep its electrons the most, right, out of anyone else. That's what we're essentially looking at here. Helium wants to keep its electrons. It's going to take a lot for it to get rid of an electron. So if you look at page 153, there's a table that gives ionization energies. And they generally follow this rule, right? As you increase to the right and you move up, you'd see a bigger number of ionization energy. Okay? Do you also see how some of the ionization energies are just lines, like they don't even have a number? Okay, so look at like francium, the total opposite of helium. Francium doesn't even have an ionization energy. And that's because francium will give away its electron to anyone and everyone like no problem. Okay? Think about what francium looks like. Francium has 7 shells of electrons. The positive charge is not pulling it close, right? It has the biggest atomic radius, right? We discovered that last time. Francium has the largest atomic radius. So its electrons are farthest away from its control center, right? Its nucleus. Do we agree with that part? So it really doesn't care what happens to its outermost electron. Okay, if you think about francium, francium has 7 shells and it only has 1 electron in that outermost shell. So it's pretty happy getting rid of that electron so it can be a complete shell underneath. Okay, do you remember talking about valence electrons? Valence electrons are outer shell electrons. And in group 1, they only have 1 valence electron in that outer shell, right? They have 1 in that s orbital. Do we see how this is all kind of coming together? Right? Francium would be like 7s1. So we know that it has 1 electron in its outer s orbital. Is that making sense? So it wants to get rid of that electron so that it can just have a full shell underneath there. Right? Francium will give away its electron. So it doesn't require like any energy at all. But helium, if you look at helium over here, helium has 2 electrons in its s orbital, which is full. And it's so close to the nucleus. So it's hanging on to those electrons with all it's got. Right? It does not want to give them away. So it requires a lot of energy. Okay, does that kind of make sense? As you see things move to the right on the periodic table, we talked about how atomic radius is pulling those closer, right? The number of protons is pulling those electrons closer as you move this way on the periodic table, which means it does not want to get rid of those electrons. See, elements on this side of the periodic table generally have a charge of +1, generally have a charge of +2, +3, plus or minus 4, -3, -2, -1, and neutral. Okay? So if these guys generally, or they want to have a charge of +1, that means they really want to get rid of their outermost electron because that will give them that +1 charge. If I know this group always wants to have a -1 charge, does it want to give away an electron or does it want to take in another one? They want to take in another one because they want to have a -1 charge. So they're not going to give away their electrons very easily. So that's why they have such a high ionization energy. Okay, what questions do we have here? All right, so the official definition of electron affinity is the energy, is the energy change that occurs when a neutral atom accepts an electron. So the way I like to think about electron affinity is how likely oh my goodness, I can't spell today. How likely an atom is to accept an electron. Okay, and when you accept an electron, that would make it what type of an ion? Good, a negative, which is called an anion. Okay, accepting a neutral atom that accepts an electron would make it an anion. Okay. All right, so electron affinities, what I want you to think about is how likely an atom would be to accept an electron. Okay, and the reasons that an atom would accept an electron would be to complete its shell, right? That's the reason that an atom would accept an electron. So what elements or what atoms do you think would be likely to accept an electron? There's a whole group on the periodic table that should be most likely to accept an electron. Any ideas? Knowing what we know about valence electrons and knowing what you know about completing a shell, which elements only need one more electron to be happy? Yeah, group 17. Right? That group, the halogens in general, have the greatest electron affinity. Because this, I'll pull up the periodic table again here so we can see it, but that group has 7 valence electrons. Okay, this group is like always going to end in P5, right? And P can hold 6 electrons. It wants another one to complete its shell. Right? It has 7 valence electrons. So if it has, well, you really can't see that, sorry. It has 7 valence electrons. So if we know we want 8, it only needs to pick up 1. So it's really, really, really likely that it's going to accept an electron. So it has a high electron affinity, which means the trends for these kind of look like this. These are the highest, and it increases as we go toward those halogens. That's kind of how I draw that trend. Electron affinities are highest in the halogen group, right, or group 17, and then they increase as you move toward that group. Page 157 has a table with electron affinity values, and I want you to look at that table quickly here. 157. Yeah. Yeah, good. Okay, if you look at the table on 157, what do you notice about group 18? They all have a 0 electron affinity. Why would their electron affinity be 0? Do they want to accept an electron? No, they already have a complete shell. There's no reason that they would take on that electron, right? So you can even cross that group out if you want, but those don't have electron affinities because they don't want to take on electrons. There's no energy change. They don't bond with things very easily, right? The noble gases, they don't bond. If they do, they bond with themselves. Okay, so there's no reason for them to accept an electron. So no electron affinity there. If you look at group 1, I want to review valence electrons really quickly. Group 1 has 1 valence electron. Group 2 has how many valence electrons, do you think? 2. And then 3, 4, 5, 6, 7, and 8, right? Do you remember those valence electron rules? Valence electrons are outer shell electrons. Okay, are we on the same page with this? Okay, so if hydrogen, or this group 1, has 1 valence electron, so if I have a hydrogen atom here and it's got 1 valence electron, is it likely to take on another one and have 2 electrons, or would it rather just get rid of the 1 electron it has? It would rather just get rid of the 1 electron it has, and it would rather just become H+, right? Which is where that +1 charge for this group comes from. Lithium wants to get rid of its outer shell electron. That way it has a full shell underneath. Sodium wants to get rid of its outer shell electron and leave it with a +1 sodium. Okay, do you see how those things kind of run together or work together? All right, so electron affinity increases as you go to the right. Okay, toward the halogens, and then after that, no. All right, our last trend is something called electronegativity. Anyone heard of electronegativity before? Okay, not so much. Okay. Electron affinity and electronegativity are similar. Not the same, but they're similar. And electronegativity, it tells the ability of an atom It tells us the ability of an atom within a chemical compound to attract electrons from another atom within that same compound. So here's the trend for electronegativity. Electronegativity increases to the right and up. I guess you could write it like this, to the right and up toward fluorine. Okay, I like to just write it as a diagonal arrow, but it's all pointing toward fluorine. Fluorine has the highest electronegativity. Okay, fluorine has the highest electronegativity, and then I'm going to explain why that is here in a second. But fluorine has the highest electronegativity. Okay, so I'm going to show you kind of a non-realistic model here of fluorine. But there's fluorine with its s orbitals. It's got 2 electrons in it. And then here is the next level of electrons. And this is non-realistic, but I'm just showing you. Fluorine has how many valence electrons? It has 7 valence electrons. Okay, so here's its 2 in that first shell, and then 7 in its outermost shell. Agreed with that? Fluorine should have 9 electrons total. That's what I have in our diagram. Okay? If fluorine has 7 electrons, does it want to give away 7 or does it want to take in 1 more? What's it want to do? To become a complete octet and become completely happy, does it want to take in 1 electron or does it want to get rid of 7? It wants to take 1 in, right? And we talked about that with electron affinity. It's really likely to take in an electron. So it's going to take in this extra electron, right? And it's going to take it from anyone and everyone because it has the highest electronegativity, right? We call it the highest electronegativity. It's likely to take electrons from any other atom because its outermost shell is closest to the nucleus, which means it has the greatest draw. Okay, it pulls it in the closest. So if I had a bond between fluorine and potassium, right, there's a bond. Each of them contributes an electron to this bond. Okay, so here it forms this bond. Fluorine wants electrons so badly that it will pull potassium's electron toward itself. So maybe now both the electrons in that bond are shaded towards fluorine instead of being shared evenly. Does that make sense? It pulls potassium's electron even closer to itself. So now instead of it looking like this, electron on one side and electron on the other, it looks like this. Both of our electrons are pulled toward fluorine. Does that kind of make sense? Fluorine wants electrons so badly, it will take them from what atoms they're just bonded with, right? It'll pull them close to themselves. That's what electronegativity is. How badly does it want to take an electron from something else? Okay? So electronegativity is really the simplest trend. It increases as you move toward fluorine. And that scale is on page 161. 161. Okay, so you see here most of those noble gases, at least the first 3, don't have electronegativity values because they don't want to take electrons from anyone, right? And they won't. Francium has the lowest electronegativity value because francium doesn't want to take electrons. It wants to give its outer electron away. So there's no reason that it would pull electrons toward itself. It's not going to attract electrons. It wants to give it away. Okay? What questions do we have about any of our 4 periodic trends?